perfect diagonal. It's like 45 degrees right there. That's called the identity function. You plug in 1, you get 1. You plug in 2, you get 2. Plug in 3, you get 3, right? So if I go to any point on this graph, what's the slope of the tangent line? 1, right? Does that make sense to you? The derivative of x should be 1? So the derivative, treating x like the independent variable of x itself, is 1. So we could have rewritten this where the x kind of pops up here with the d and looks like this, dx over dx. And does it make sense to you that that would be 1? Or you could do it this way, x prime equals 1. Derivative of a constant. Derivative of constant? Derivative of x. Okay, we continue.
If you put any number in front of x, it would just be that number.
Yeah, we're going to, it's coming. Yeah. I'm just going to go through them in order. So this one right here is the next big one. The power rule. The almighty power rule, all right? Look at what this rule says. It says that if we wanted to find the derivative, if our function was x to any power, that would be the derivative, n times x to the n minus 1. So I did this in class last time, remember with Pascal's triangle? And I did this problem. I said do this, and I said find the slope of the tangent line at x equals a. I did that in class. We did it. I used Pascal's triangle, and we got an answer. It was n times a to the n minus 1. You can look in your notes. That's the answer we got. Do you all see that this is exactly the same formula, except we've replaced a with what? X. Okay? So I've actually proven this to you algebraically, why this is true. So now I'd like to show you this in action. All right? This rule in action. This rule goes like this. Let's say I take x to the 4th power and I ask you to find its derivative. All you're going to do is take that 4 and do what? Pop it out front, and then put x, and now you're going to put up here what? 4 minus 1, which will be 3. So 4x cubed. And you're done. You don't have to do any limits. You don't have to do any of that crap anymore. You've got the rule. Super shortcut, right? Let's do another one. X to the 70th power. Take the derivative. 70. X is 69. Done. Right? Nothing else to do. Isn't this nice? No limits. So there's a pro and con to this, because the good news is we have a shortcut that we can avoid limits. The bad news is that now I can start giving you more complicated functions. Right? So how about this? Put a star next to this. Put 3. Let's go with 5 stars next to this. Okay? Because no matter what, I've been teaching this for years and years and years. Students will come into this class, they will have learned calculus before, and then when we get to this one, they do it the way that they were taught, which is not a problem, but then later on they're confused because I'm doing it a different way. I'm going to show you the way I do this, and then you either take it or not. It's up to you. Let's use this rule. Can we use this rule? Okay, what's the power on that x? 1/2. Okay, so first, before we even do a derivative, I'm going to put x to the 1/2, and then I want the derivative. Now I can use the rule, right? N for us is what? 1/2. So I'm now going to take derivative, so no more derivative mark, right? I bring the 1/2 out. X to what power? I have to take the half and subtract 1. Okay, subtracting 1 from a fraction is something that you have to get fast with, all right? When you're first learning this rule, you're going to kind of struggle with it a little bit, but you really need to get used to taking a fraction and subtracting 1. And to do it, all we ever do is just get a common denominator. So you just rewrite the 1 as 2 over 2, and that way you can subtract them. And now you just do numerators, 1 minus 2 over 2, and that gives you negative 1/2. So this should be 1/2 x to the negative 1/2. Y'all agree? And a lot of students will learn it that way, and I'm not saying it's wrong. That is correct. But I'm going to keep going with this, all right? Remember in algebra that a negative exponent means you can drop it down, all right? So I'm going to rewrite this as 1/2 times, and now I'm going to drop that down as x to the 1/2. So I drop this down, put a 1 on top of it, and then I'm going to multiply straight across, and I get 1 over 2, and then this, doesn't that just mean the square root of x? Isn't x to the positive 1/2 the root of x? So I get 1 over 2 root x, right? I strongly urge you, implore, is that a word? Yeah, implore? Is that the right word for what I'm trying to say? I implore you to try and memorize that derivative, because I'm going to use it a ton in this class, and you'll use it a ton in Cal 2 as well. Let's say it together. The derivative of the square root of x is 1 over 2 root x. The derivative of root x is 1 over 2 root x. The derivative of root x is 1 over 2 root x. The derivative of x is 1 over 2 root x. I can't say it fast, but I can say it right. Derivative of root x is 1 over 2 root x. All right, let's do another one. How are we doing on time? Plenty of time. Still got, what, 2 hours?
No.
It's not 2 hours? Okay, what about the cube root of x? So maybe it's 1 over 3 cube root of x, right? No, that's not it. This is the only one that works like this. We have to actually grind this one out, all right? So that's really x to what power? 1/3. And now you can use the rule, right? So you bring out the 1/3. X to the, now I take the 1/3 and I subtract 1. But that's the same as doing 1/3 minus 3 over 3. Do y'all see it in your head?
Yeah.
1/3 minus 3 over 3. Do the 1 minus 3 up top and you get negative 2/3, right? So 1/3 x to the negative 2/3. And that, if I drop that down, is going to be 1 over x to the positive 2/3. Yes? Pardon me? Oh, cube root of x. Yeah, I was going to ask you, what does this mean? Right? What does that mean? These, whenever you have something raised to a fraction like that, those are called rational exponents. And when you convert it to a root, that's called radical notation. In calculus, we need to be able to go back and forth between the two, all right? But truly, calculus students, we really love to work with rational exponents as opposed to radicals, because the power rule is better if we have a number up there instead of roots. So I'm going to write the answer, even though I was technically done right here, but I'm going to keep going and put, you said the cube root of x squared, right? What's that property? X to the fractional power m over n equals the nth root of x to the m. That's the way that rule works. If you have a fractional power, then the denominator is what root you're taking, and the numerator is what power is on the x. So that's the rule, and that's why I did this. All right, good? We're not done. We're going to keep going with this power rule. Let's just see an honest show of hands. How many of you have seen the power rule before? Look at how many people have seen the power rule, right? So you've all suffered through the limit, and you're like, okay, let's get on to the rule, because you knew it was coming, right? So I'm going to put a new one up here, and let's see if I can't trip anyone up. So I'm going to put an answer up here, and I want you to tell me what I did. And I'm going to do it in red because it's wrong. But I want you to tell me what I did. Okay, who wants to tell me what I did? Yeah, what did I do?
Took the derivative of the top and then the bottom.
I did the derivative of the top and the bottom separately, right? What's the derivative of 1? Well, 1 is a constant. Derivative of a constant is 0. And then derivative of root x is 1 over 2 root x, because I'm learning that. It's like a little song, right? That's what I did, right? And 0 over anything should just be 0. So I box up my answer and I say 0, and I'm wrong, right? So what makes this wrong? I did the derivative of the top and bottom separately, right? Who told me I could do that? Nobody, right? Have I told you you can do a fraction like that? No, you're not allowed to, all right? Unfortunately, you are not allowed to do that. In fact, when it comes to fractions, we have an entire rule of how to deal with fractions. It's called the quotient rule, and it is truly what makes calculus hard, is that things don't work the way you wish they would work. You wish that you could just do derivative of top and bottom, don't you? Wouldn't that be nice? If you just do top and bottom, just get an answer? But it doesn't work that way. Yes?
Is that the one where it's low D high times high D low?
It's taught that way sometimes, yeah. It's like a little song? Yeah. Okay. So this is wrong, right? This is wrong. So the question becomes, what's right then, right? How do I do this problem? Well, the only rules I have at this point are this. The derivative of a constant is 0. The derivative of x is 1. And then the derivative of x to the n is that power rule, right? That's all I have. Bring that power rule back up. Power rule. Right there. That's all I have. So the only hope I have at this point to do this is if I can write that as x to a power. If I can get it as x to a power, then I can use the rule. So I'm going to just manipulate this algebraically first. I'm going to take this and rewrite as 1 over x to the positive 1/2 power, right? I'm trying to take derivative. And then I'm going to push the x to the half up into the numerator by rewriting it as x to the negative 1/2. I want the derivative of that. You see how I've transformed it from a fraction into x to a power. Now I can use the rule. But see, my power is what? Negative 1/2 instead of 1/2. So that whole little cute thing I was trying to get you to learn with the 5 stars next to it doesn't apply. You're just going to use that rule. So what number comes out front? Negative 1/2. Then I have x to the, careful, negative 1/2 take away 1. That's what you're doing, right? You're subtracting 1 from negative 1/2, which is? Negative 3/2. Negative 3/2. Doing negative 1/2, take away 1, right? That's negative 1/2, take away 2 over 2. Negative 1, take away 2 is negative 3. So you get negative 3/2 here. And this time I'm just going to leave my answer like this. The only one I really want you to get to like a radical is the square root, right? The one that I said, what's the derivative of square root of x? 1 over 2 root x. Let's just learn that. That's the only one I really want you to ever get back to a radical. The other ones like this, you could have just left it here. I'd be okay. All right? You all good? Let's do one more. How about 1 over the 5th root of x cubed? Take that derivative. I cannot do the derivative of the top and bottom separately, can I? All I can do, if there's any hope, is to rewrite that as x to a power. So I can rewrite that as what?
1 over x.
Okay, 1 over x to the 3/5, you said? 3 over 5. And then that I can push up as x to what power? Oh, forgot the prime, sorry. X to the negative 3/5. I need the derivative of that. Yes? You got it? You got the answer? Okay, everyone caught up though?
Yes.
Go ahead.
Negative 3/5 x to the power of
Negative 8 over 5, 8/5. That seems right. You bring the 3/5, negative 3/5 out. I'll do it down here. Negative 3/5 comes out. X to the, now you take negative 3/5 and you subtract 1, right? So you could just right now do 5 over 5 if you want. And that'll give you your negative 8/5. All right. I changed my mind. We're going to do one more. Two more. This one's going to be real fast, though. What's the answer? 1. Does the power rule work here, though? What's the power on this? It's 1. So let's try the power rule. What happens? Bring the 1 out. X to the 1 minus 1, right? 0. So you get 1 x to the 0. And x to the 0 should be 1, right? 1? So 1 times 1 is 1. So that's just to verify that it does work, right? This is the one I really wanted you to do, though. X cubed over the 7th root of x squared. Can you do the top and bottom separately?
No.
Why not? Why can't you do the top and bottom separately?
Doesn't work that way.
Yeah, I'd never told you you could, right? And right now you can only do what I've told you to do, right? Everything else, don't make any assumptions. So what I'm going to do here, x cubed on top, on the bottom, x to the 2/7, right? Not 7 halves, 2/7. Then I'm going to use properties of exponents, right? No calculus yet. This is just properties of exponents. I'm going back to that rule from college algebra, x to the m over x to the n. What do you do with these? Subtract, right? M minus n. That's the rule. So I'm going to take this. Oh, I forgot my prime. Sorry. Take that. This is going to be x to the 3 take away 2 over 7. And then I still need to take derivative, don't I? What is 3 take away 2 over 7? Yeah, 3 take away 2 over 7 is the same as 21 over 7 minus 2 over 7, common denominator. That's 19 over 7, yeah? So you got to be able to manipulate some fractions here. You get better. Calculus forces you to either drop the class or get better at fractions. There's no way around it. You have to be able to manipulate them. All right, so we have x to the 19 over 7, and then we want the derivative. So now we can use the rule, right? Finally? Mm-hmm. 19 over 7 comes out. X to the what is it?
Negative 26 over 7.
12 over 7. 12 over 7. 12 over 7. So what we're doing there is 19 over 7 minus 1, right? And I'm going to rewrite 1 as 7 over 7. And now you can, 19 minus 7 is 12. So there we go. Okay. We're good? We had another hour. So we have another hour. All right? He didn't show up. I invited him. So what are you going to say about that? All right, so that's the power rule. You ready for the next rule? That is the most important rule in this section, right? The power rule is the big one from here. Now we have, I'm going to make this a little bigger. We have what is called the constant multiple rule. This rule's a little weird because when you see it the first time, you're like, what the hell is this saying? So I'm going to write this rule in a slightly different way than it appears up there. Let's say I take a constant, and let me just call that constant c. So c is some number, right? It's fixed. C could be 10, 5, negative 2, pi, whatever you want. Let's say I take some constant, and I multiply it times some function. All right? And then I say, all right, take the derivative of that. This rule says that what you can do is you can pull the constant out front and then just take the derivative of the function and multiply the answer. So I call this bringing the constant for the ride. It's like you have a constant in front of a function. What you're going to do is bring the constant for the ride and then just take the derivative of the function. Example. Do you see a constant times a function of x? Okay, so your constant is 5. You're trying to take the derivative. This rule says that I can bring the constant with me, right? 5. And now, just take the derivative of the x to the 7th. You see? What's the derivative of x to the 7th? 7 times, so I have a 5 out here, 7 times x to the 6th. And then 5 times 7 is 35. X to the 6th. All right? That is the correct way to do it. Here's a student that did this. What did that student do? They took the derivative of each of these separately, didn't they? They did derivative of 5, 0. Why? Derivative constant 0, right? Times the derivative of this. But what did they assume? They assume that when you have a product, right, that you can do the derivative of each one separately. Isn't that what they assumed? I never said you could do that, right? I've only shown you that the derivative of a constant is 0 by itself. Constant by itself, derivative is 0. Derivative of x is 1. Derivative of x to a power is n, right? The n, x to the n minus 1. We already saw that if you have a quotient, you can't do them separately. So what would make you think that if you have a product, you can just do them separately? You can't. We have a rule for that. It's called the product rule. It comes after our test. All right? So this is no. All right? This is the proper way to do it. Use the constant multiple rule. The constant comes for the ride. Then you take the derivative. And in this case, I mean, you could have just looked at it in the very beginning, like just the 7 comes out and hits the 5, right? Just becomes 35 x to the 6th. All right. Next rule. Sum and difference rule. This rule says that if you are adding two functions together, adding or subtracting two functions, and you're trying to find the derivative, that yes, it does what you hope it would do. And that is you can do the derivatives of each of them separately and then add or subtract their answers. This rule is nice because it behaves exactly the way we wish it would. I'll give you an example here. What if I had x to the 3rd plus x to the 4th, and I wanted to take the derivative? Can I use this rule?
Yes.
Yeah, because what I have here is essentially two functions. I have like an f here, then plus a g, right? Two functions, and we're trying to take their derivative, and they're being added together. This rule says, well, then what you can do is find the derivative of the f, then find the derivative of the g, and then add those two answers together. See, isn't that the way that you would hope it would be? Yeah, that's exactly what it is. So let's do these derivatives. What are they? 3x squared plus 4x cubed, and we're done. We're done, right? We're done. Okay, yes? Let's look at our quiz problem from today. Our quiz problem from today was f of x equals x squared minus x. And I asked you for f prime of a, didn't I? Which means take the derivative of that. Well, let's get rid of that. Let's say f prime of x, because now we know we're going to just dump the a and replace it with x. Let's find the derivative of that. So let's do it. When we take this derivative, what we're going to see is on the right-hand side, we have subtraction between these two, right? It's because there's subtraction between the two, I can take the derivative of each one. So I can do my x squared, take its derivative, subtract from that the derivative of x. What's the derivative of x squared? 2x. And then minus, what's the derivative of x? 1. And what was our answer on the quiz? 2a minus 1, right? 2x minus 1. Like that, right? We just get it like that now. No more limits. Isn't that nice? How about the problem off of the review? Where was that one that we did? Yeah, it was this one. I had f of x equals 3x squared minus 4x plus 5, right? And what did I ask for here? The second derivative, right? The derivative twice. The derivative twice. But I said use the definition, right? So I had to use the limit, right? I had to use the limit. And so what I showed you on this problem earlier is the way I'd want it done on the test. But what you could do now that you have the shortcuts is what? Use the rules and check your answer, right? So what answers did we get for this? It was 6x minus 4, right? And the other one was just 6, right? Okay, so let's do this using the shortcuts. The derivative of this should be, okay, can we do them separately? Yes, because there's addition and subtraction. So I'm going to take 3x squared, I'm going to take its derivative, minus the 4x, I'm going to take its derivative, plus the 5, I'm going to take its derivative, right? I do each one separately. That I'm allowed to do because I just gave you the rule, the sum and difference rule allows us to do this. And now, what's the derivative of this? 6x. The 2 comes out, 6x. Okay, what's the derivative of this? How are you getting 4? It is right, but I just want to talk about why is derivative of this 4?
Because the x is 1, so it's 1.
There's different ways to look at it, right? I'm going to look at it this way. The 4 comes for the ride, right? The 4 comes for the ride. And then what's the derivative of x? 1. Or you could say there's a 1 here, and the 1 comes out, hits the 4, becomes a 4, and then x to the 0, which would give you 1. Either way, everyone should be comfortable with the idea that the derivative of 4x is 4. So minus 4, and then derivative of 5? 0, right? So that's the answer we had, right? A lot less work. And now the second derivative is now the derivative of this, which is a difference. So I can do derivative of each one of those. Derivative of 6x is 6 for the same argument that I made there on the 4x. And then derivative of a constant is 0, so we just get 6. You see how easy it would be to check my answer? Right? So then, I mean, students will always ask them, why do we have to go through all the limit stuff, right? Why do we have to do all that? Why do we have to torture ourselves with all these limits? Well, it gets harder. It should always work. Like it should. The reason really is actually a little different. It's that if we didn't do all the work with the limit, then you'd be more of like in a business calculus class, where all we do is just like feed you the formulas, and then you start using the formulas to do something. Here, we torture you with the limit because you need to be able to handle limits, because in terms of like level of difficulty, limits is up here, basic rules are down here. And so later on, it's going to get harder in this class. And if you don't have like a baseline of what in your mind is difficult, then it just kind of comes at you too fast. I don't know if that makes sense. You're trying to, in the beginning of calculus, make sure that the students are mature enough to handle the difficulty, so you give them the limits so that they can grind through them. And then later, we'll go back to limits again. We're going to revisit them. So it's just a more rigorous treatment if you do limits. All right, what's the next one? What is that saying? The derivative of the sine function is the cosine function. Now, I'm actually going to prove this one to you. And I'm going to do it 2 different ways. I'm going to do it visually first, and then I'm going to do it with the limit. I'm actually going to torture us with the limit. And then after I prove this one, I won't prove any of the other ones. You're just going to be like, we believe you, okay? So I'm going to start with the graph of sine of x. Going back to pre-cal, I'm just going to draw one period of sine. It's 2 pi here, it's pi. What we're looking at here is the function f of x equals sine x. Right? Think about what we did at the beginning of class today, where I was saying, let's draw its derivative, right? Let's draw its derivative. At what points do we know what the derivative would be? At what points here on this graph?
At 0, pi, and 2 pi.
At pi over 2 here, what's the derivative here?
1.
No, that's the value of the function. What's the slope of the tangent line here?
0.
So my derivative should be here, right? And then here at 3 pi over 2, the derivative should also be 0, shouldn't it? So it should go here. Do y'all agree those blue points are on the derivative? Okay, now let's just play this game where we kind of move along here. If I'm at the top here, what should happen is I'm starting to move to the left. My derivative is what? Positive or negative? Positive, getting bigger, bigger, and bigger until we get to here. Now my drawing's not very good. The slope of that line right there, when I stop there, is actually 1. The slope is 1. So it was 0, it's small positives getting bigger until I get to 1. You know what I should do so that it looks right? Graph it. That way everything looks perfect here. All right. So in Desmos, if you come over here to your x-axis and you put step on here and you put pi over 4, let's say, it'll change all your coordinates to radians. All right, so take a look at that. We were saying here at pi over 2, the derivative should be 0. And then here at 3 pi over 2, the derivative should be 0. I guess what I'm trying to get you to see with using the computer is that right here at this point, does it look to you like the slope of that tangent line is 1? Does that look like a perfect diagonal to you? Yeah? Yes, yes? Somewhat? 1? So that means it's there. So what happened? It was 0, small positives, and then it gets bigger positives, right? So it actually looks like this. Small positives, bigger positives until we get to there. And then when we go this way, it's what? Small negatives till we get to right there. What does the slope of the tangent line there look like? Not 1, but -1, right? So it should be small negatives until we get to -1. This was +1. And then it's going to be still negatives, but going back to 0, right? So it's negatives going back to 0.